Welcome back to our discussion of simple and multiple regression. Next, we'll take a look at Chapter 14 in the Yaki text about multiple regression. As we showed in the last chapter, we're going to start with a comparison of simple and multiple regression. And so you'll recall on the left here we have that same example that we used in the discussion. And on simple regression, our basic research question is, do scores on one variable predict scores on the other? In this case, we had test A and test B. Recall that there is one set of null and alternative hypotheses. That is that the standardized regression coefficient is equal to 0. In other words, the slope of that line is basically 0. And then the alternative hypothesis would be that the beta regression coefficient, or sometimes called the beta weight, is not equal to 0. And that regression coefficient, the unstandardized one, just the regular b, not the beta, that indicates the slope of the line of best fit in the metrics of the measures that were used. And it also tells you the expected change in your dependent variable for a 1 unit increase in the independent variable. So that's something we talked about fairly extensively before. And then finally, we had an effect size of an r squared. Essentially, that's the Pearson r squared for those two variables and those measures. And that tells us the proportion of variance in the dependent variable that's explained by the variation in the independent variable. So that's just a brief review of what we saw in simple regression. Multiple regression is very similar, but as the name implies, we have more predictor variables. So as a diagram here, we no longer have a bivariate scatter plot, but instead now we have three axes. We have an x-axis, a y-axis, and a z-axis. So on one of these axes is our dependent variable, and so that represents the dependent. Then we have our first independent variable on another axis and the second independent variable on the final axis there. And so you can see, instead of a flat scatter plot, now we have a three-dimensional cloud of data points that are based on three measurements on all three of these instruments or whatever's used to collect the information, and they're each plotted for each individual participant in the particular study. So in this chart, the lighter colored points, the red points, are closer to you. The darker colored ones, the black ones, are further away. So they're attempting to try to illustrate this three-dimensional nature of it. And you'll also notice that there's a plane that determines the best fit for those three-dimensional data plots. Rather than having a single line, now since we're in 3 dimensions, we need a plane. That plane does cut across the y-axis at the dependent variable, and that is our intercept. So we have an intercept just like we had with the simple regression, but now it's where the plane intercepts the axis for the dependent variable. Let's take a look at some of the things that are included here. Our research questions now, in this particular example, we would actually have three. The first one is, does the independent variable 1 predict the dependent variable? The second is, does IV2 predict the dependent variable? And then the last one is the entire model. So instead of looking at individual independent variables, now we're looking at them as an entire model. They're lumped together. So taken together, do IV1 and IV2 predict the dependent variable? So the number of independent variables you have in your multiple regression will determine the number of research questions you're going to have. If you add an extra one, you would actually have 4 research questions, one for each of the 3 independent variables and then one for the overall model. Looking at the hypotheses, as you might expect, if we have 3 research questions, we have 3 sets of hypotheses that we're looking at. The first one has to do with the beta weight for independent variable 1, saying that that's equal to 0. The alternative is that it's not equal to 0. Then you can see the second set there. That's for the second independent variable. Is its influence on the dependent variable significant or not? And then finally, that R, capital R squared, which is called the multiple R squared, that represents the overall model. So that answers the question, taken together, do the 2 independent variables predict the dependent variable. So that's our third test that we're going to do in evaluating the results of multiple regression. Then in terms of the coefficient, we have the B's, which are the unstandardized coefficients, and those indicate the expected change in the dependent variable for a 1 unit increase in the independent variable, taking into account all of the other variables. So as if you held the other independent variables constant, we're just looking at the isolated influence of one independent variable. And so that's what the coefficient tells us. We also have an effect size. Now we have the multiple r squared, and again that is based upon the full model with all the independent variables included, and that tells us the proportion of variance in the dependent variable that's explained by all of the independent variables. So hopefully you can see that while multiple regression is a little bit more complex, if you understand simple regression, we're just basically adding some independent variables. It adds and increases the number of research questions, but basically it follows the same sort of design that we learned about in simple regression. So next, let's just take a step back and look at the overall big picture of multiple regression. Our big objective is that we want to be able to predict scores on a dependent variable using scores from 2 or more independent variables. So you could have 2, 3, 5, 27. You could have a lot of independent variables. The more independent variables you have, though, the larger the data set that you need. Typically, for every independent variable, you should have 15 to 20 participants, so that's a good rule of thumb to use for that. What are the requirements of the data? The dependent variable or the criterion variable needs to be on a continuous scale, whereas your independent variables could either be continuous or they could be dichotomous. So as we saw for simple regression, it could be like male female or yes no, or those types of dichotomous variables. Then there are some assumptions, of course, for multiple regression. The first is that the observations are independent, that the individuals participating in the study are not influenced by each other. Then there's this assumption of multivariate normality. That's a little bit difficult to explain, but basically what you're looking at is all of the variables being normally distributed at each level of the other variables in combination. So just by even saying that sentence would indicate how complex figuring that out is. So it's very difficult to actually establish that, but if you have a large enough sample size, according to Yockey, the assumption of multivariate normality it's okay to violate that to some extent. Then we also have this idea of homoscedasticity. You recall that from simple regression. We talked about the variance in the independent variables being consistent across all levels of the dependent variable. So that is yet another assumption. Again, Yockey talks about that in terms of if you have a large enough sample size, that's not a problem. So bottom line here, several times we've talked about sample size. So with multiple regression, large sample sizes are really essential. So next, let's look how you might predict a score on a dependent variable in multiple regression. Like we saw in simple regression, we had a y hat, which is our predicted value on our dependent variable. Then we had this a, which was our intercept, the y-intercept. Then we had unstandardized regression coefficient b. Now, since we have multiple independent variables, we give each one of those a subscript. So b1 times x1 would be for the first independent variable, b2 times x2 would be for the second, so on all the way through as many independent variables as you had. So each independent variable has a term that has a slope and the variable itself, and you're going to have as many of those terms in your regression equation as you have independent variables. Now in the example I just gave you, we had 2 independent variables, so the equation would be shortened down to this. So we're interested in figuring out what's the intercept, what's b1, what's b2, so that we can create our multiple regression equation so that we can predict what our outcome variable, our dependent variable, might be. So suppose our intercept was 10, and then b1, our slope or our coefficient for the first independent variable was 0.5, and for the second it was 0.7. So we can take those numbers and plug those into the equation. So you can see now here we've got the intercept and both of those regression coefficients in there. If we knew some values for an individual person on x1 and x2, we could plug those in. So we're going to say, suppose a person scores us, these are three tests, a 60 on test 1 and a 40 on test 2. What would we expect this person's score to be on the third test, or the dependent variable, based upon the model we've created? So plugging those numbers in here, so here's the same equation, and then all I've done is put 60 in there for x1 and 40 in there for x2. You get your calculator out, you crunch the numbers, and you come up with 68. So the predicted score on the dependent variable would be 68 if x1 was 60 and x2 was 40. So this is how you can use multiple regression to predict the outcome. So here's a question after all of that. Here's your question. It is, how much of a change in test 3 scores would you expect for a 1-point increase in the test 1 score? So the question that's in your mind is, well, how do I figure that out? So we're obviously talking about test 1, so somehow it's got to do with x sub 1. And notice that the regression coefficient is 0.5. And so that tells me that if my score on the first test, test 1, goes up by 1 point, I would expect my score on test 3 to go up by a half a point, 0.5, taking into consideration the other variable that's there, the x2, or the other test score. So if the other test score was held constant, I would expect a half a point increase if I got 1 point higher on test 1. So let's take a look at the Yaki example for chapter 14 before actually working through it. He has four variables actually. The dependent variable is something called meaning in life, and so that's some measure of whether you have meaning to your life. Then there's 3 independent variables. One is about connectedness to other people. The second one is about optimism. The third one is about academic success. So we've got 3 independent variables and 1 dependent variable. So since we have 3 independent variables, we're actually going to have 4 research questions. The first one is, does connectedness predict meaning in life by itself? Does optimism predict meaning in life by itself? Does success predict meaning in life? So those are the 3, 1 for each of the 3 independent variables. And then our fourth question is about the entire model. Taken together, do connectedness, optimism, and success predict meaning in life? So those are the 4 research questions that we're going to be looking at. And so since there's 4 research questions, again, we're going to have 4 sets of hypotheses. So looking along the first row here, we can see the null hypothesis, the beta for connectedness is equal to 0. And then below that, the alternative hypothesis is that the beta for connectedness is not equal to 0. Okay, and then going across, we have the second hypothesis that the beta for optimism is 0, then the beta for success is equal to 0, and their alternative hypotheses. And then looking at the very end of each of those 2 lines there, you see we have the hypotheses that address that last research question. Is the overall model predictive of meaning in life? Do all 3 of those variables together. So we're going to use the multiple r squared to do that. So the null hypothesis is that our multiple r squared is equal to 0, and the alternative is that multiple r squared is not equal to 0. Okay, so that lays the groundwork for the example in Yaki. So next